All right, today though, talking about Thanos' favorite chapter, chemical equilibrium, or balance in all things. So most things exist not as a static balance, like two things weigh the same, but as a dynamic equilibrium. So there's two opposing processes that occur at the same rate. For example, if you're riding your bicycle and you're pedaling as fast as you can, the rate of you trying to accelerate is countered by the rate of basically wind resistance pushing back on you. So you can maintain that speed as long as you can pedal hard enough to counteract the force of the air friction, which is why like professional cyclists wear Lycra, because it has the lowest wind resistance. It's also like a freeway with traffic moving in opposite directions. Is a chemical equilibrium in which the two opposing reactions occur at the same rate. So cars are going down the freeway one way, cars are going down the freeway the other way. If there's the same number of cars moving at the same speed, then if you were to stop at any point in time, you know, all the cars on one side, there'd be the same number of cars there as on the other side.
Like the energy pumps, right?
The what?
Like
Oh, yeah.
Kind of?
In cells, yeah. Yes. So related to this, obviously, is the rate of a chemical reaction. So a chemical system is at equilibrium when the rate of the forward reaction, or the cars driving one way down the freeway, is equal to the rate of the reverse reaction, or the cars driving in the opposite direction. The rate of a chemical reaction is a measure of how fast the reaction proceeds. Usually we talk about it, I mean, you can think about it as moles of something converted per second or hour. It's kind of like a rate of speed. You're going a certain number of miles every hour. But it's also the amount of reactant that changes to product in a given period of time. So reaction rates can be controlled if we understand the factors that influence them. It's on my screen, sorry. Collision theory states that chemical reactions occur through collisions between molecules or atoms. So if you have hydrogen and you have iodine, they're not going to react unless they collide with each other. So you can think about one of the things that's going to mediate how fast our reaction proceeds is how often the molecules we want to react, or we're interested in the reactions of, how often they run into each other. So there are a few things also that go along with that. If they just gently bump into each other, there's not enough energy for them to react. So they have to collide with enough energy, which we usually think of temperature. So they have to collide with enough energy for the reaction to proceed. That collision energy is related to particle velocity. So that's going all the way back almost to kinetic molecular theory, where the temperature is related to the speed of the particles. For gas phase molecules, have a wide distribution of velocities, so collisions occur with a wide distribution of energies. This is also that graph that I showed you, or that I drew, where you have like this sort of shape. And then the reason that we're running out of helium is that some of those particles of helium are going fast enough to leave Earth. So high energy collisions lead to products, but low energy collisions do not. Right? So they have to really run into each other. Most chemical reactions have an activation energy. So that's the amount of energy that we need to get above. So if we have a diagram like this, and this is energy, we're going to have some barrier, right, some bar, some point at which the energy of these two particles colliding needs to go over that to get to the products. We'll see more diagrams like that. So most chemical, have a activation energy. That activation energy may be the energy required to begin to break the bonds of the reactants. So in the case of, right, if we have hydrogen reacting with iodine, these bonds between the hydrogen, iodine, those need to break before new bonds can form between a hydrogen and an iodine to get the two products. So we can use this as a starting point for the factors that we can control or the factors we need to understand for how reaction rates, or what makes reaction rates what they are. The factors that influence the rate of reaction must be the same factors that affect the number of high-energy collisions that occur per unit time. So anything that's affecting how often these collide, so how often they collide, how much energy they collide with. So those are two sort of major factors that are like the underlying theory for why reaction rates are, for what determines what reaction rates are. So the rate of reaction generally increases with increasing concentration of the reactants. Right? So if we have more things to react in the same amount of space, they're going to be colliding more often. So we've increased the number of collisions. And as that reaction proceeds, though, the concentration of the reactants is going to decrease over time, because every time they react, they're used up and they're turned into products. And so that reaction rate will decrease over time. So this diagram on the right, you have something with a low initial concentration, and that's going to have a slow initial rate of reaction. If we have this intermediate, that's going to be an intermediate rate, and a high concentration is going to be a fast initial rate. But as these start to react and are used up, then it'll slow down to the same rate as the intermediate concentration's initial reaction rate. And then as those react, eventually we'll get down to this low concentration. So as we start to use up our reactants, there's fewer things to collide. Fewer collisions means fewer reactions. Another thing that we can modify to increase or change the rate of a reaction is the temperature. So temperature determines how fast the particles, especially of a gas, are moving. So if they're moving faster, they have more energy. So when they do collide, they'll be more likely to react. So if we raise our temperature, then we have, well, actually, in addition to that as well, in addition to higher collision energy, they're moving faster, so they're more likely to have a collision as well. So you're going to get double the effect there. And again, this diagram on the right is just saying low temperature. So particles have short speed lines or blur. These ones are moving faster and then even faster. So higher temperature, higher reaction rates. So to summarize, our reaction rates generally increase with increasing reactant concentration and with increasing temperature. I'll highlight these. So increasing reactant concentration, increasing temperature, and then as a reaction proceeds, reaction rates generally decrease. Because if we're starting, so if this is our reactant concentration, if we start with a high reactant concentration, we're also going to have a high rate. But if this is time, as this reaction proceeds, a reactant concentration is going to decrease. And so eventually, or I guess not eventually, but along with that, the rate will decrease because of this first one. reaction rates generally decrease as a reaction proceeds. So in a chemical reaction between two gases, you would expect that increasing the pressure of the gases would probably. I've been taking an online teaching course, so we're going to try something new today. We're going to try something new. Figure out what you think it is, and then talk to somebody next to you and tell them why you think it's one or the other. And I'm just going to give a couple minutes for that. So we increase the pressure of the gases. You're sitting on an island. Hard to find somebody to talk to next to you. This would work way better at the beginning of the year. You have some time to work on people and get people to talk to each other. All right, so if we increase the pressure, how does that affect our two factors here, right? Number of collisions and energy of collisions. Yeah, so if we increase the pressure, depending on if we also keep the volume the same, I guess I'm assuming that we are, we have to also increase the temperature. So temperature is going to increase. Pressure also means that there's more particles present. So we're going to be increasing the number of particles present as well as the temperature of those. So our reaction rate will increase.
So why are we increasing the temperature too? Like
That was the,
hand in hand or what?
yeah.
Oh, okay.
So we've increased, actually I should say, we had some pressure here, we had some temperature here. If we increase pressure, then this side of the equation has to equal the same thing as the other side still. So temperature also has to increase. I guess I can leave that on there. All right. So up until this point, we've really talked about reactions in just a single direction. They proceed until they are done, until we've used up all of our reactants. More often than not, though, that is not the case. Usually there's some equilibrium. So there's some amount of your products that are reacting with each other to go back to reactants. And this is a reversible reaction. So most reactions are reversible to some degree, but it can proceed in both the forward and the reverse directions. So if we have hydrogen and our iodine again, these two can collide and then react to form hydroiodic acid. But these hydroiodic acid molecules can also collide with each other and go backwards to hydrogen and iodine. So when we're talking about these reaction rates and the rate of the forward reaction and how it relates to the rate of the reverse reaction, this is a dynamic equilibrium. So our forward, when we are at a dynamic equilibrium, the forward and reverse reactions are still occurring, but at the same constant rate. So the relative concentrations of our reactants and products doesn't change anymore either. Right? This is like the cars again on the freeway. There's the same number of cars going the same speed in either direction. If you stop at any point in time and you look to your right, you're going to have the same number of cars on the right as on the left. And for a reaction at equilibrium, it's not necessarily going to be 50-50. But the rate will be the same. You can freeze time, and there will always be the same number of particles as products as there are as reactants. And yet, if you start time again, they'll continue to react, forming reactants and products. So equilibrium is reached when the concentrations of the reactants and the products no longer change. All right, so we've reached balance. But equilibrium does not mean that the concentrations are equal, just that they stop changing. So we look at this reversible reaction, again, hydrogen and iodine. I'm going to zoom in over here. We'll zoom back out in a second. So when this reaction starts, it's all hydrogen and it's all iodine, right? So T0. If we let 15 minutes pass, though, now we've ended up with 6 hydrogen, 6 iodine, and now 4 hydrogen iodides. If we let it go for another 15 minutes, then we've got 4 hydrogens, 4 iodines, and 8 hydrogen iodides. And then we know that we've reached equilibrium because if it goes for another 15 minutes, our number of each, our amount of products and the amount of reactants hasn't changed, even though they're still reacting in the forward and reverse directions. Oh, I forgot about this slide. So the rate of people moving, so if you have Narnia next to Middle Earth, separated by a river, you have, the rate of people moving out of Narnia slows down as people leave, right? So if all these people are unhappy here, they want to be on the other side because, hey, it's a lot less crowded in Middle Earth. So they're moving over to Middle Earth. Narnia starts to be less crowded, but Middle Earth starts to get more crowded. So at some point, these people are going to want to move back to Narnia because they're like, I don't like the number of people here. Maybe I got a new job opportunity over there. There's this constant influx of people. But at some point, this is all going to balance out. I don't remember what this video link is.
Say two people are walking down the street to each other. They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if two people were to bump into each other?
Okay, so that's a nice video that explains in a fun way chemical equilibrium. So at equilibrium, again, our rates of the forward reaction and the reverse reaction are the same, but not the concentrations. So what are the concentrations at equilibrium? We can use an equilibrium constant, and we can actually calculate at equilibrium what the relative distribution of concentrations is going to be. So our equilibrium constant is Keq. So if we consider this generic chemical reaction, right, we have A, B forming C and D. The equilibrium constant, Keq for the reaction, is defined as the ratio at equilibrium of the concentrations of the products raised to their stoichiometric coefficients divided by their concentrations of the reactants raised to their stoichiometric coefficients, which probably just sounds like word salad. Simply put, we put the concentrations of the products and we divide by the concentration of the reactants, multiplied by each other. So you can see that we have C and D, that's C and D, and then their coefficients, if any, well, if something other than 1, we raise them to that power. So it's always products over reactants. So we want to write an equilibrium expression for this reaction. Right, we have 2 N2O5, so dinitrogen pentoxide, decaying into nitrogen dioxide and oxygen. So we put our concentration of our products, and again, I guess these are gases. You can do molarity for gases, kind of. Concentrate, or the brackets like this, always means concentration. And it's usually molarity, which again is moles per liter. So we've taken the nitrogen dioxide and oxygen, those are on our numerator, so the top of this fraction. And then nitrogen dioxide gets raised to the 4th power because that's the coefficient in front of it. Oxygen gets raised to the 1st power, but if you raise something to the 1st power, it is itself. So we leave that as an implied 1. And then our reactant is now in our denominator, and again, raised to the power of its coefficient. This is very formulaic. This is the way it is every time. Well, I say that, but you don't put solids, liquids, what was it? Solids and liquids aren't part of the equilibrium expression. Mm-hmm.
What does the implied mean?
So because there's not actually a 1 in front of the oxygen, there's an implied 1 there.
Got it.
All right, so if we want to write an equilibrium expression for this chemical equation, then we'll have KEQ. And actually, I should write that a little more. This is a subscript EQ. Is going to be, I'm going to do it like this. We're going to go products over reactants. So KEQ is equal to, all right, so our product here is hydrogen fluoride, all right, HF in brackets, and it has a coefficient of 2, so we raise it to that power. And then we're going to have our reactants in the denominator. So it's going to be H2 brackets multiplied by F2 in brackets. Yeah?
If they're interchangeable, does it matter which one's a product versus reactants?
It does, because KEQ is for the reaction in this direction, or set up this way. So KEQ will boil down to a number like 1.1 times 10 to the, let's call it 10 to the 5. So because this is a big number, this is saying there's a lot more of the product than there is of the reactants. But you could flip this, and then it would be for the reaction written the other way. Are there any other questions? Good? Oh, and I just made this number up. So, well, I just said this, but when KEQ is a large number, that means you have a lot of products compared to your number of reactants, right? So if we take, So if we take this KEQ here, for example, it's 1.9 times 10 to the 19. Huge number. Essentially what you're saying is for every, if you have a concentration of 1, units don't really matter, a concentration of 1 of hydrogen and of bromine, right, because that's going to equal a concentration of 1. They have to have a 1-to-1 to react together. You're going to have 1.9 times 10 to the 19 is going to be your concentration of your hydrogen bromide. Right? So you're going to have, I don't even know what 10 to the 19 is, way past quadrillions even. Right? So you're going to have this extremely large number of product and almost none of your reactants. So that's reacting almost completely. But there will be some tiny portion of reactants still. When KEQ is a very small number, so we have 4.1 times 10 to the negative 31, then we have more reactants than products at equilibrium. So in this case, it would be like saying, if we had, a reaction, let's say 1 molar is our concentration of nitrogen monoxide, and then the product of, I'd have to take the square root of that. But on the bottom, we're going to have the product of these two, so the concentration of N2 times the concentration of O2 is going to equal 4.1 times 10 to the 31, say molar. So there's going to be 10 to the 31 of these nitrogen and oxygen, but just 1 nitrogen monoxide. Yeah.
When do you use these, when do you use this in science and the real world? Like this type of equation and stuff, what is the purpose of it?
A lot of it would be, I'm trying to think if you would use it exactly in this form, because you could calculate the KEQ for any given reaction at a number of different temperatures to figure out what is the temperature dependence of this. And it also means that I guess you do need to know the relative. But then if somebody else wanted to do the reaction, you could say this is the KEQ at this temperature. And if you increase the temperature, the KEQ gets higher because it produces more products, and that might produce better yields if somebody else is doing the reaction. So it's probably something. Research chemistry.
What's that?
It would be like research chemistry.
Okay.
Formulations chemistry probably.
Okay.
You use this also this is also very similar to acids and bases, because talking about pH or POH is kind of like an equilibrium.
Mm-hmm.
It's the product of the two. Process chemistry. That was what I was trying to think of. Process chemistry is in a huge factory, if you're making 1 million gallons of ammonia every day, you need to know exactly what these ratios are so that if you're producing a lot of waste, you're not going to use that process. Because if you're producing 1 million gallons of something, you're going to produce a lot of waste. So a visualization of what a large equilibrium constant looks like. If hydrogen bromide divided by the concentrations of hydrogen and bromine is a large number, then most of these are hydrogen bromide. And we only have 1 each of the hydrogen and the bromide. For a small equilibrium constant, the opposite is true. So if you were to look at the actual molecules of your reaction, you'd have just a couple here that reacted, and the rest of them are unreacted. So in summary, if we have a very small KEQ, the reverse reaction is favored. You're going to have more of your reactants than you are products. If KEQ is about 1, neither direction is favored. So the forward reaction proceeds about halfway, and you'll get significant amounts of both reactants and products present at equilibrium. And then if our KEQ is large, the forward reaction is favored, and the forward reaction proceeds virtually to completion. So if we have a solution of, a heterogeneous equilibria, so if we have reactions involving a solid or liquid, those are taken into account differently. So the concentration of pure solids and pure liquids are excluded from equilibrium expressions, because they are essentially constant. So if you have some solid in a solution, not dissolved in the solution, just like at the bottom of the beaker, it's not really interacting with that solution. And so any amount of it that is in the solution is going to react, but as soon as it's reacted, then more of the stuff that's undissolved can hop into solution. And so you essentially have an unlimited reservoir of reactant as a part of that reaction. So because this equation would be, right, with two solids here, this would be, if we were to write the KEQ with the solids in it, the KEQ, our concentrations, so it's products over reactants. So this concentration would be infinity, multiplied by the concentration of CO2, divided by, in this case, the concentration of infinity, because both of them are essentially in infinite proportions to the rest of the solution. So we leave those out. In this case, they cancel, which is nice. But that won't always be the case. So our reaction, our K equilibrium, is only dependent on the amount or the concentration of CO2. So if this number is a large number, the only thing that we really know is that we have a lot of CO2. If it's a small number, then we don't have very much CO2. All right, so solids and liquids are emitted. So if we wanted to write an equilibrium expression for this, again, we've got products over reactants. We can just identify up front which of these are liquids or solids, right? So HCl gas, oxygen gas, H2O is a liquid, so we're going to leave that out. But we have chlorine, that's also a gas. So our only product we're going to include then is going to be the concentration of chlorine, raised to the second power, because it has a coefficient of 2, and then HCl raised to the power of 4 times oxygen with that implied coefficient of 1.
Is that all the time? Like they're always going to be made?
Yep.
Can you tell me why solids and liquids are emitted? Okay.
Yeah, because they essentially act as an unlimited reservoir. So if you're doing a reaction in water, then almost everything is water, and there's a very tiny amount of the other stuff.
What number do you put in for each element? You would put molarity, like if you're doing calculation?
Yeah, so that would be usually molarity, or it could be molality, or it could be any concentration unit.
Do you need to solve for this, or is it just that's how it is? This is what it looks like?
No, we'll get there.
Oh, okay.
Yeah. And again, this will work like, any of the other equations that we've had really, where you'll be given concentrations of everything but one thing, and you have to calculate. Yeah.
I'm still stuck on the solids and liquids.
Sure.
Why they matter sometimes and right now they just don't matter. Or
So why they matter? Like if we were to do a reaction, if we had a reaction equation, and I gave you the mass of solid magnesium reacting with HCl to produce hydrogen gas, you would use that then to calculate how much you could make in that situation. Is that what you're talking about? But in this situation, we just leave it out. Yeah. So here we're talking about equilibrium, where things are going to balance out too. So if we have essentially an unlimited amount of a solid, then that rate or that concentration is not going to change the rate of the reaction at all, because it's never going to change. So it would be, okay, so yeah, for this, we left out the water, but it would have been, actually I'm going to do it in a different color. So if we wrote this out, right, CO2 squared, H2O squared, right. So this is our reaction, or equilibrium constant. If, in this case, water is essentially infinite, the concentration never changes. So I put it in here to show that it looks ridiculous when you add it in there, because now our equilibrium is infinitely towards water, because there's way more water than anything else. But really what this is talking about is this. Let's look at it like this. So if we look at the concentration, this is our Cl2 concentration. If we throw into this solution, basically if we throw a bunch of chlorine into the water, our rate of reaction is going to be, or our concentration is going to be high, our rate of reaction is also going to be high. As that chlorine gets used up and turned into reactants, right? So if we're going in the reverse direction, that's going to change, or that's going to increase our concentrations of HCl and O2. So as that reaction goes, it's going to slow down because we're running out of chlorine. If we added more water to this, it wouldn't change anything. If we took a little bit of the water out and changed the concentration of the water, it still doesn't change the equilibrium, because we're limited by, I guess this is kind of a limited reaction problem, we're limited by the amount of chlorine, and that's what's determining the rate. Does that help, or was that more confusing? Okay. We can keep moving, because we're going to start, I think we're going to talk a little bit more about this. I think there is, they shared that PHET, P-H-E-T, there's that website that has a lot of really cool simulations.
I tried to do that last time, but it was really difficult to maneuver. Did anybody else get it?
I haven't played around with it too much. I just know for Chem 10 they have labs from it. I think there's an equilibrium one on there. So you can play with these things, and I feel like the easiest way to see how water, liquids, or solids don't participate in the chemical equilibrium is to look at some actual numbers and see that if you change those numbers, it doesn't change anything. So equilibrium constants also depend on temperature. So if you think about it, if you increase the number of collisions, that can affect one side of the reaction more than the other. So it's not part of the equilibrium equation itself, but the temperature does have to be specified. Concentration should always be in moles per liter, which is molarity, but the units are normally dropped. Oh, the concentration. Yeah, I mean, they're dropped because sometimes they'll end up weird. But the concentrations will not always be the same, but equilibrium constant is the same at a given temperature. And again, we'll see more how that applies if we start throwing some numbers in. Do you need more time on that one? I'm sure there are others. All right. So if we have, this is a good example of an actual question. I mean, probably give you a question that says, write out the equilibrium constant, or equilibrium equation for this reaction. Definitely a question you could get. But in terms of numbers and word problems associated, Suppose a mixture of hydrogen and iodine is allowed to come to an equilibrium at 445 degrees C. The measured equilibrium concentrations, so these are the concentrations of each of the reactants and products at equilibrium at this temperature. So we've got 0.11 molar hydrogen, 0.11 molar iodine, and our hydrogen iodide is 0.78 molar. So what is the value of the equilibrium constant? So the keys here really are, right, so we have a mixture is allowed to come to equilibrium at 445 degrees C. The measured equilibrium concentrations are given, and we want to know what the equilibrium constant is. So this is where we can put this together, and we can put together the equation to calculate that. So we're going to get K EQ, right, is again our products over reactants. So hydrogen iodide squared, and our concentration of H2 times our concentration of I2. Yeah.
The big M's
Molar.
so that can change.
That can change. I'm always going to give it to you in molar. Yeah. Molar, which is again,
And for heat, is it always going to be in Celsius?
this temperature, the temperature just has to be constant. Yeah, so it's not going to be part of the equation, and I'm not going to, we're not going to cover an equation that allows you to convert the equilibrium constant from one temperature to another.
Okay.
I'm not even sure if that exists. Yeah, so the temperature is actually not actually one of the very important things here, but it's the fact that it comes to an equilibrium.
Right.
So once we have this equation, and we have our concentrations at equilibrium, we can just punch those numbers in and calculate what KEQ is. So HI is going to be 0.78 squared. And we're going to have 0.11 times 0.11. So 0.78 squared divided by 0.11 times 0.11. So let me double check that. Oh, yeah, that did not do what I wanted it to. You got to be careful with these. If you type it into your calculator like I did 0.78 squared, and then I did divide by 0.11, and then I just typed times 0.11. And that's going to do it in the wrong order. So make sure you're careful with that. And use parentheses. So it's going to be 50.3, I guess, two significant figures, so 50 decimal. Or it'd be better to write as 5.0 times 10 to the 1. So again, usually the units are left off because here we would end up with inverse molar. So 50 is like not a super large KQ, but we are going to have more products than reactants, or actually 50 times. Oh yeah, this is a good diagram. So if we've got an initial concentration here of hydrogen, iodine, and hydroiodic acid, or hydrogen iodide. our initial concentrations, it's all hydrogen and iodine. When we come to equilibrium, we're going to get actually the concentrations that we just saw. And then we can calculate KEQ, and it's going to be 50. If we change our initial concentrations, and we have just 0.5 molar hydrogen iodide, when we come to equilibrium, we're going to have different concentrations than we had up here. But when we plug those into this equation, it's going to spit out 50 again. Because KEQ is just the relative amounts of products versus reactants. So again, we can put in 0.5 molar for all of them. It's going to balance out again according to the equilibrium. And then our equilibrium constant calculated from that number is again going to be 50. So it doesn't matter what the initial concentrations are. Once it comes to equilibrium, our KEQ is going to be the same. So if we have this reaction, where we have a mixture of carbon monoxide, hydrogen, and methanol is allowed to come to equilibrium. Again, that's a key word. Allowed to come to equilibrium at 225 degrees C. The measured equilibrium concentrations are given there. What is the value of the equilibrium constant at this temperature? So again, we're just writing KEQ. Always want to be checking. These are all gases, so we don't have any liquids or solids, so we're not going to leave those out. But this is going to be methanol. So product is methanol. And then our reactants are going to be carbon monoxide times hydrogen. And then hydrogen is going to be squared. So again, we can just punch these numbers in. So methanol, 0.151 over carbon monoxide, 0.489 times our concentration of hydrogen, 0.146 squared. 0.151, 0.489 times 0.146. We're going to get 14.5.
And how, is that it? We don't have to write units at the end of it, or what are the units for it?
Nope, that's it. If you want to write units, you can write molar, I suppose. But it's weird because we have, this is in concentrations of molar, molar, molar. So if we were to do like we normally do, where we cancel out the units when we divide,
Right, that's what I was wondering.
yeah, like this is cancels, but then this is molar squared, so this would actually be, again, 1 over, oops, capital M, molar squared. So the units are kind of arbitrary. Partly because it is a proportion. So it's just the proportion of products divided by reactants. Were there any questions there?
So, we just know that that's the product then CH3OH, right?
Yeah, because it's on the right side of the reaction arrows. Which I don't think it pointed out, but you'll notice these reaction arrows, there's one arrow pointing the forward, one in the reverse. Okay. So we can also use KEQ to calculate the equilibrium concentrations of one of the reactants or products, provided that we have the concentrations of the others at equilibrium. So if we have this equation, we're given a KEQ at 1,000 degrees Celsius. And we're also given, and these questions would be written like, at equilibrium, the concentration of this is this, and the concentration of this other thing is this other thing. What is the concentration of the last one? So here this is our equilibrium concentration of, what even is that? Oh, it's fluoroacetate. Anyways, COF2, and then CF4, or tetrafluoride, carbon tetrafluoride. And we want to find the concentration of CO2. So again, we can write our KEQ, our equilibrium concentration equation is going to be products over reactants. So CO2 times the concentration of carbon tetrafluoride divided by the concentration of COF2 squared. I think that's fluoroaldehyde. So from here, we can plug those numbers in that we've been given. So for KEQ, we're going to put in 2.00 is equal to, we have this COF2 is going to be 0.255 squared. The concentration of CO2, which is what we're looking for, and the concentration of carbon tetrafluoride, 0.118. And then it's just algebra from there. So, oops, I don't really have space for this. So I'm going, taking this up here. I'm going to do 2.00 times 0.255 squared. That's going to be 1.3. Sorry. The calculator's doing everything in scientific notation. So now that's equal to CO2, concentration of CO2 and 0.118. So I can divide that 0.13005 by 0.118 and get 1.10. And here you can't put a concentration, or can't put molarity as the concentration of CO2. Cool. So we have diatomic iodine decomposing at high temperature to form iodine atoms, according to this reaction. So again, these keywords of equilibrium. So in an equilibrium mixture, so we're working at equilibrium, the concentration of I2, iodine, molecular iodine, is 0.10 molar. What is the equilibrium concentration of iodine? So we've been given a KEQ. We've been given one of the concentrations. So we can write our equilibrium equation. It's going to be products over reactants. This is I squared over the concentration of I2. So if we sub in these numbers, we get 0.011 is our KEQ. Our concentration of I2 is 0.10. And this is I squared. So we do 0.011 times 0.1, and then we take the square root of that. So the square root of, so it was, just to show you these steps, 1.1 times 10 to the negative 3 equals, yeah, concentration of I squared. So we take the square root of both sides, we get 3.3 times 10 to the negative 2 molar equals the concentration of iodine. This part? Do the square root.
Oh, got it, okay.
All right. So we talked about things at equilibrium. What happens if we disturb that equilibrium? Le Chatelier's principle is a description of that. It's kind of like not exactly a law, it's a principle, it's a little weaker than a law, but when a chemical system at equilibrium is disturbed, so if we change the temperature, if we add something to it, if we take something away, the system shifts in a direction that minimizes the disturbance. So a system at equilibrium fights back when disturbed. Move on. So if we have, again, Middle Earth and Narnia, probably didn't know that they're right next to each other. The population, if we add population to Middle Earth, Sauron's just spawned a whole bunch of more Uruk-hai. It's all really crowded now. We've added more people to Middle Earth. So if we increase the population there, all of these people originally moved to Middle Earth from Narnia because Narnia was crowded. And now Middle Earth is getting really crowded again. So they move out to the other side. They move out to minimize the disturbance. So if they can reduce the population here, they can go to somewhere else where it's less populated already. So if instead there was a giant war that broke out in Middle Earth and a bunch of people have been removed, to put it mildly, then there would be fewer people in Middle Earth. So there's a lot of space, and the people from Narnia can move over there. So this applies also to reactions.
Why don't they just live in the river?
Honestly, I don't know. Boat people, I don't know. So if we add, when product is added at equilibrium, the rate of the reverse reaction increases. Because we've increased the concentration, more collisions can happen, so that rate speeds up. So we add here, and then it shifts to the other side to reduce that concentration. And it reduces that concentration because the reaction rate has increased. So we shift away from the side that we add to. I think it's also, if you can think about two, well, I guess it'd be like, looks like pants, but if there's water in here, so there's water on this side and there's water on this side, that's sort of at an equilibrium. If you dump a bunch of water in here and raise the level up so that it's over that middle bridge, it's now going to move over to the other side to balance out. It works better actually if there's like a, this may be less intuitive, but if there's like a, right, 2 buckets connected with a pipe in the middle. So then the water level in these, because they're connected, is going to be the same. If we take water out of one side and reduce this level, then water is going to flow from the other side to bring them back to level. This is actually the problem that we had with the lab where we generated and quantified hydrogen gas. If you left one beaker too low, then the levels weren't the same, and water would flow through the siphon to the other side to make the levels the same. And then if you pick that beaker up, or pick up one of the flasks higher than the other one, you've essentially disturbed that equilibrium, shift it the other way. So in this diagram here, we're adding NO2, like we did on the previous slide. And when we add that NO2, the equilibrium's disturbed. And so the system shifts to the left. So more of this NO2 is going to break down, or actually combine, into N2O4. So adding reactant, so if adding product caused us to shift to reactants, adding more reactant will cause us to shift to the products. Because we're increasing the forward reaction rate. What's the top one here? So if we increase this forward reaction rate, because we've added more products, added more reactants, more collisions can happen because the concentration's higher. The rate speeds up, and then it will slow down eventually so that we come back to a constant state. So you're essentially breaking the equilibrium. So here if we add, these are the N2O4 molecules. If we add these in, we've disturbed the equilibrium. Now there's more N2O4 than really what the equilibrium equation, or the equilibrium constant would dictate. So they break apart to balance out. So if a chemical system is at equilibrium, and we increase the concentration of one or more reactants, that will cause the reaction to shift in the direction of the products. If we increase the concentration of one or more of the products, then we'll shift to the reactants. So you're filling up one side, and it needs to drain into the other side to level out. All right, so if we have this reaction at equilibrium, and we add more bromine to the reaction mixture, bromine is one of our products, which way is the reaction going to shift? Yeah, if we add a product, we're going to, most simply put, we're going to shift the reaction left to the products, or to the reactants. If we add more, this bromine nitrogen oxygen compound, bromonitrous, what is the effect of adding more of this bromine nitrogen oxygen compound on the equilibrium, or on the reaction, not the equilibrium? We're going to shift the reaction, to the right. Shift the reaction right to the products. So if the process of adding something, shifts away from the side that we've added it to, then what is the effect of removing some bromine? Yeah, it's going to shift now to make more bromine. So if we add more, or if we remove bromine, it's going to shift the reaction right. Okie doke. Let's finish this thing off. Doing a lot this week, so you have a lot of time next week to just study or do stuff for other classes. Well, we're going to do the last 2 chapters this week, and then we're going to do like, oh yeah, you weren't here at the beginning of the class. We're going to have like review sessions next week, basically. And I think I do want to do like, have one of those be, you can come in and I'm going to like go through the chapters and essentially pick out the concepts that I want to be on the exam and probably record that and post that. Okay. So, right, so we're looking at, right, if we change the concentration, that's going to cause our equilibrium to shift. It's fine. So wait for you to take the picture. Or you can also change the volume, and that will change your equilibrium. The reason it changes the equilibrium comes back to the factors that change our rates of reaction in the first place. So decreasing volume increases pressure. So if we increase pressure, the molecules are going to be closer together. And you're going to have more collisions. And also should increase the temperature as well. If we increase volume, we've suddenly given the same amount of particles, larger space to fly around in, so they're less likely to collide. So a decrease in pressure is going to decrease the rate of reaction. Also, lowering the number of moles of a gas results in a lower pressure at constant temperature and volume. So one of the ways that a system can relieve pressure, so if you increase the pressure, it can relieve that pressure by converting those moles of gas into, well, usually aqueous something or a solid or a liquid. So if it removes those gas particles from the air, that's going to decrease the pressure. So decreasing volume increases the pressure. Right? This is why a bike pump works. You're taking a long cylinder, and you've got a plunger at the top, and you're pushing it down, and that pressurizes the air because you're moving a large volume of air into the smaller space of your tire. So to bring pressure back down, if there was a reaction happening, the equilibrium shifts. I'll highlight this one. So to bring the pressure back down, the equilibrium shifts to the side of the reaction with fewer moles of gas particles. So this is where you have to look at your reaction and say, I'm going to zoom in on this. So we've decreased the volume. On the left side, we have a total of 4 moles of gas particles. On the right side, we only have 2 moles of gas. So we can essentially condense these 4 moles down into 2 moles. And by removing those moles of gas, or taking 4 particles, making only 2 particles, we're reducing the number of particles present and thereby the pressure as well. So a decrease in volume causes an increase in pressure. And to relieve that pressure, the system shifts to the side with the fewer number of gas particles.
So it doesn't necessarily become less, though, of any at all?
It's not less of like the total, like the mass would be the same. But it'd be like, yeah, it's condensing. Yeah, exactly. So it's like if you went to Disneyland and everybody like stayed like exactly 6 feet apart, right? That's going to take up a lot more space than what it used to be at Disneyland, where everybody just like walks shoulder to shoulder in a giant mob. So that takes up less space, though. So if you can reduce that, then you don't need as much space and less pressure.
Does it always shift to the product side, or can it go either way depending on?
It could go either way. Yeah, it depends on the reaction. So that's where you got to count the moles of gas on each side, and it'll shift to the side with fewer. And the reverse is true as well. So if we had this system pressurized, if we then, and then of course the reaction is going to shift to decrease that pressure. If we pull that plunger back up and we increase the volume, now the pressure is too low, and so the reaction is going to shift to the side with more gas particles to fill that space. Which is what this slide is. So again, if our volume, an increase in volume decreases pressure because we have fewer particles in a larger space, same amount of particles in a larger space. So to oppose the decrease in pressure, the equilibrium shifts to the side of the reaction with more moles of gas particles. So to summarize, decreasing volume increases pressure and causes the reaction to shift to the side with fewer gas particles. Decreasing, fewer. If we increase the volume, then we're going to shift in the direction that has more gas particles. And then if the moles of gas particles on both sides of the chemical equation is equal, it will have no effect. Because by shifting to one side or the other, the reaction is not going to change the amount of pressure. So if we consider this reaction at equilibrium, what is the effect of decreasing the volume of the reaction mixture? This would be volume decreased, which means pressure is going to increase. So to relieve that pressure, we want fewer particles. So we're going to shift. We're going to shift to the products. Because on the reactant side, we have 3 moles of gas particles, and on the product side, we only have 2 moles. So if we increase the volume of the reaction mixture, so we have volume has increased, so pressure has to decrease. So we want more particles to shift that pressure back. Then we're going to shift to the reactants. All right, so we talked about now, we can change concentrations. All right, if we add concentration to one side, it shifts it to the other side. If we remove concentration, it wants to sort of shift to fill in that space. We can change the volume, which affects the pressure, and that shifts reactions to the side with, if we increase if we increase volume, we want to shift to the side with more moles. If we decrease volume, shift to the side with fewer moles. We can also change temperature, because again, this is all related to increasing or decreasing the number of collisions and increasing or decreasing the reaction rates. And temperature is one of those things that changes the reaction rate. So for exothermic reactions, we can think of heat as a product. And so if you have a fire burning, it's generating heat, so one of the products of that reaction you can think of as heat. So if you raise the temperature of an exothermic reaction, it's like adding heat to the product side. And if you increase the concentration of the products, the reaction is going to shift to the side of the reactants. So adding heat to an exothermic reaction will actually cause it to shift to the left. In an endothermic reaction, though, heat is now not one of the products, but it's endothermic, so it's sucking up heat as it reacts. Heat is now one of the reactants. So if we raise the temperature of an endothermic reaction, it's like adding heat to the reactant side, and the reaction shifts to the right. So if we have a reaction, or exothermic reactions, if we have heat, right, is one of our products because it's exothermic. Adding heat into this reaction is like increasing the concentration of the products. And so our reaction shifts left or to the reactants. If we have the same exothermic reaction and we are able to remove the heat from the reaction, so you've got a heat sink or you've got a fan blowing on it, or put it in a refrigerator. You're doing something to remove the heat from the reaction. That's like reducing the concentration of one of the products, and we shift then towards the products. So the key for these is remembering exothermic reactions, heat is a product, endothermic reactions, heat is one of the reactants. So for an endothermic reaction, and if we add heat to the endothermic reaction, it's like increasing the concentration of a reactant. And so we shift away from that increase to form more products. If we remove heat, actually this is a cool reaction, but if we remove heat from this reaction, it shifts to the left. You actually take these two gas, well, really you can just take one gas, put it into a flask, and you can heat it up and the gas turns brown, and then you can cool it down and the gas becomes colorless again. So for endothermic reactions, heat is a reactant. For exothermic reactions, heat is a product. And if anything, you can remember exothermic reactions because fire is an exothermic reaction. That produces a lot of heat. Oh, there's a reaction. So there's a vial of the dinitrogen tetraoxide. So as you warm it up, it turns brown, and then you cool it down, and it becomes clear again. So you can force this reaction. It's the equilibrium is dependent on the temperature. So you're shifting the equilibrium back and forth just by cooling it up or cooling it down or warming it up. I almost said this backwards. Cooling it up. All right, so exothermic, heat is a product. Endothermic, heat is a reactant. And then it just ends up being the same as changing the concentration of your products or reactants. So we're given here, the following reaction is exothermic. So heat is one of our products. So what is the effect of increasing the temperature of this reaction mixture? Shift to the left. Everything you own in a box to the left. So what is the effect of decreasing the temperature? Shift it to the right. Electric Slide's the only song that I can think about shifting to the right. So if you get one of these questions on the exam, make sure you just figure out exothermic, endothermic, and then write heat on the side that's appropriate, and then treat it like increasing or decreasing the concentration of heat. Okay. Shift gears a little bit. There are a lot of things that are dependent on equilibrium. Solubility product constant, or solubility really, is one of those. So the solubility product constant is a better way of quantifying how soluble something is, especially if it's very, very not soluble or insoluble. So this is the equilibrium expression for a chemical equation that represents the dissolving of an ionic compound. So if we were to take a solid and dissolve it in water, this is the equilibrium for how much will dissolve. Again, solids are emitted from the equilibrium expression. A large Ksp, right, so before we had Keq, that was equilibrium. Ksp is solubility product. So solubility product, Sp. If we have a large Ksp, that means the compound is very soluble. If we have a small Ksp, that means the compound is not very soluble. So if we write the equation for our chemical reaction involving the solid compound in equilibrium with its dissolved aqueous ions, in this case we have barium sulfate dissolving into barium ions and sulfate ions. Our equilibrium then, or Ksp here, or solubility product, is just the ions, concentrations of the ions multiplied together. Because we would have, right, the concentration of the barium sulfate here, but it's a solid, so we leave that out. So Ksp is this sort of a special case of equilibrium constants, where your one reactant is a solid, and you're quantifying how much of it dissolves. So for these compounds that are really insoluble, we can have a Ksp that quantifies exactly how much of it is going to dissolve when it's in solution. So right, they're like 10 to the minus 10, 10 to the minus 9, very, very small numbers. Okay. So if we wanted to write a solubility product constant equation for silver iodide, we're going to have silver iodide, and it's going to be dissolving into silver plus iodide. These will both be aqueous. So our solubility product then, Ksp, it's going to be our products over reactants, but because our reactant here is solid, we just have silver times concentration of iodide. So then for calcium hydroxide, again, we can just write our reaction arrow in here. This is a solid. And we're going to have calcium plus 2 hydroxide ions, because there are 2 hydroxides that are part of calcium hydroxide. So our Ksp then is going to be the concentration of calcium times the concentration of hydroxide squared. We have a 2. Yeah. Right, over here, yeah, it's a subscript. But because we have 2 hydroxides there, when it dissolves, we'll get, yeah. All good. Any other questions there? No? So the solubility of a compound is the amount of compound that dissolves in a certain amount of liquid. The molar solubility is the number of moles of a compound that dissolves in 1 liter of solvent. Right? So molarity is moles per liter. Molar solubility is also moles per liter. But specifically for solubility products, it gets abbreviated as S. Oh, now I remember this is the one. So remember how to calculate molar solubility. Because I want to say that the molar solubility is the amount of, oh. Now we could Google it real quick. Let's try and figure it out. So 1 times 10 to the negative, 1.77 times 10 to the negative 10. That's our Ksp. Molar solubility is the number of moles of a compound. It's the number of moles of silver chloride that will dissolve. I think that, and we'll check this on Google in a second. So our Ksp, let me do it this way, right? Because our Ksp equation, Ksp is equal to, it's going to be the concentration of the silver times the concentration of Cl minus. So if our Ksp is 1.77 times 10 to the negative 10, then really this is going to be, think about it like this. For each one of these silver chlorides that we have, we're going to get 1 silver ion and we're going to get 1 chloride ion. So really, this is the molar solubility squared, or Ksp is, because we've multiplied the concentration of the silver and the concentration of the chloride ions to get this number. So I believe, and again, check this in a second, 1.77, it's the square root of 1.77 times 10 to the negative 10 is going to equal, well, it's going to equal S. So 1.77 e to the negative 10 squared. So this is 3.13 times 10 to the negative 20 molar. So the moles of silver chloride that would dissolve. So molar solubility. Aha. Figured it out. So, right, so S is our number for molar solubility. So in this case, it's the square root because we had 2 ions. It won't necessarily be that every time.
Because we haven't what?
So here, let me go back to this. So yeah, this is molar solubility. If, for example, let's shift all this over a little. Let's say that instead of silver chloride, it was magnesium chloride. So you got MgCl2. When MgCl2 dissociates in water, it's going to be magnesium 2 plus 2 Cl minus. So then our equation for Ksp is going to be magnesium times chlorine squared. But all 3 of those ions came from a single magnesium chloride. And we want to know the number of moles of the magnesium chloride that can dissolve, not the total concentration of all of the ions that it dissolves into. So to simplify this, you can say Ksp, right, so we put a number in there. Let's just call it 1 times 10 to the negative 5 is equal to, and then we replace each of these ions with X. So this is now the concentration of X times the concentration of X squared. So it's the concentration of X cubed. So that 1 times 10 to the negative 5 equals the concentration of X, which is our magnesium chloride, cubed. So if we take the cube root of 1 times 10 to the negative 5, we'll get the molar solubility of magnesium chloride. Does that make sense?
So this one, the first one was only squared because there's only 2 moles?
Yeah, there's only 2 ions it makes. So really, yeah, if you want to really like simplify this down, your molar solubility is your Ksp to whatever power, to whatever root number of ions there are. So here this is 2 ions. So S equals the second root of Ksp. Over here, S equals, because there are 3 ions, the third root of its Ksp. So if you had 4 ions, it would be the 4th root, so on and so forth. Most of the time, it's going to be 2 or 3. All right. We don't have the, oh, I guess we can use this table. Was it calcium sulfate? So Ksp is 7.1 times 10 to the negative 5. So then we want to calculate the molar solubility. So that's S. Best practice here to probably just write out the equation first, the reaction equation. So you've got calcium sulfate, solid, is going to dissociate into calcium ions and to sulfate ions. So this is where you could use this equation. And you could just say S is equal to the second root, or the square root, of Ksp, because we have two ions. But we could also just go ahead and write out the Ksp equation is calcium 2 plus, not plus, times SO4 2 minus. So each of these ions is coming from the same calcium sulfate. So we can replace these with, this is calcium sulfate times the concentration of calcium sulfate equals, well, not Ksp now, but S. And I don't know a better way to formally write this. No, it's still Ksp, but we can put the number in here now. 7.1 times 10 to the negative 5. 7.1 times 10 to the negative 5 equals the concentration of calcium sulfate squared. So we take the square root. That will equal the soluble molar concentration of calcium sulfate. 7.1 e to the negative 5. Oh wait, I squared that. I think that's what I did on the other one too. So this equals 8.4, let's call it 8.43, times 10 to the negative 3, which is S. Okay, go back here because I think I calculated 1.77 e to the negative 10. I think I squared that. Oops. Yeah, I did square that. The square root is 1.33 times 10 to the negative 10, or 5. Okay. So, we've talked about equilibrium constants. They describe how far a chemical reaction will go. So you're going to get some proportion of products relative to reactants. The reaction rate describes how fast you're going to get there. The reaction rate doesn't say anything about how far the reaction will go. And changing the rate doesn't change the equilibrium, just how fast you get to the equilibrium. So the activation energy or activation barrier is the energy barrier that must be overcome in order for the reactants to be converted into products. So activation energies exist for most chemical reactions because the original bonds must start to break before you can form new bonds. So you have to have energy to start things off by breaking bonds. So in general, at a given temperature, the higher the activation energy for a chemical reaction, the slower the reaction rate. So if it takes more energy to react, you're going to have fewer particles that have enough energy to react, so it happens more slowly. So this is a diagram that I was kind of trying to draw earlier. So if we have our reactants here, they have to get over this hill, which is the activation energy, before they can drop down to the energy of the products, which is usually a lower energy. Come on. So, to speed up a slow reaction, you can increase the concentration of the reactants, right? We add more particles, they react, they have more collisions, and a larger proportion that have the energy to react. You can also increase the temperature, so you're increasing the amount of energy present for all the collisions. And you're also getting more collisions. Or you can use a catalyst, which essentially lowers the energy of activation. A lot of different methods that catalysts can do that, but it only lowers the activation energy barrier. So you're not changing the equilibrium, you're just making it easier to get to equilibrium, and so it happens faster. So it's like if we were to try and push a boulder up a hill to roll it down the other side. It takes a lot of energy to roll it to the top of the hill, but if we had a second path, essentially that catalyst is a second path. So you don't have to go to the top of the mountain. You can go around the side of the mountain and still get to this lower energy state. So this catalyst provides an alternate pathway. And by lowering that barrier, really you're lowering the barrier to entry, more of your collisions will react because more of them have the requisite energy. So you can form your products faster. Yeah, almost done here. Many reactions are thermally sensitive, and increasing the temperature often destroys them. So, I mean, lots of things are like this. If you're trying to cook something and you heat it too hot, you, in theory, if it doesn't destroy it and burn, then you can increase the rate of reactions. But most of the time, it'll burn before you do that, and burn before you create the product. So for a lot of things, the only way to carry out the reaction is to use a catalyst. And most of the thousands of reactions that must occur for living organisms to survive would be too slow at normal temperatures. So living organisms use enzymes, which are biological catalysts that increase rates of biochemical reactions. I think, is there a picture on this one? Oh. So the enzyme sucrase is a catalyst, and it creates a pathway with a lower activation energy for the conversion of sucrose to glucose and fructose. So a lot of times what these biological catalysts do is they hold different parts of the molecule in the ideal positions for the reaction to take place. So it'll grab onto a sucrose molecule, and then by grabbing onto the sucrose molecule, that changes the shape of the enzyme to put that bond under stress between the glucose and the fructose and cause it to break more easily, or really faster. So it lowers that activation energy and increases the reaction rate.